Welcome guys to my YouTube channel Rare Science Simple, and let's make the science simple. Currently I am making lectures on population genetics. I have given few lectures on population genetics before. If you have not watched these videos, please watch them before moving forward. So without doing any delay, just let's start this topic of inbreeding. So now we need to understand what is inbreeding. So inbreeding is the mating between the relatives, that is known as the inbreeding, and these relatives, they share the common ancestors. So the common ancestry between mating pairs, that constitutes the inbreeding. Now let's understand this is by this figure, where the first cousins, where they share the same genetic information with the grandparents. When they reproduce and produce the offspring, these offsprings are identical by the descent or identical by the grandparents. And if suppose these offsprings are reproducing with each other and producing the offspring, these offsprings will also share the same allelic information with their grandparents, but this time the allelic information is going to be less in comparison to these offspring. So let's say if these are the offspring 1 and these are the offspring 2, then the offspring 2 will share less information with their grandparents in comparison to the offspring 1. So this terminology is also known as the identical by descent, means these offsprings are identical by descent, by or you can say by their grandparents in this examples. So now read this definition of identical by descent. In inbreeding, an allele is said to be identical by descent if it is inherited from a common ancestors by both parents of the individual. For example, first cousins, they share the same grandparents, here. If they reproduce, their children will inherit the same allele from the grandparents through both of their mother and father, and this is the terminology which is used in the population genetics and is called as the identical by descent. So what is the effect of inbreeding? In the case of inbreeding, the heterozygosity actually decrease, and the heterozygosity in the inbreeding is less than the heterozygosity in the random mating, and the heterozygosity in the random mating is less than the heterozygosity in the natural selection. So if you have not watched the videos on random mating, please do watch this video. In the random mating also, if with every generation the heterozygosity decrease, but the decrease is not as high as in comparison to the inbreeding. So in case of the inbreeding, the heterozygosity is very less in comparison to the random mating, and in the random mating also the heterozygosity is less in comparison to the natural selection. So let's understand this by an example, how the heterozygosity decreases from one generation to the next generation. For example, there is the example is of self fertilization. It means there is an inbreeding. So the plant is having a 1/4 capital A, 1/2 capital A small a, and 1/4 small a genotypes. After second generation, it is producing 7/16 capital A, 2/16 capital A small a, and 7/16 is small a genotypes. It means in the initial generation the heterozygosity was 1/2. After second generation, it is 1/8. It means it is decreasing. After third generation, it will again decrease. So can you prove it, how it is decreasing from 1/2 to 1/8? So let's solve this problem. For example, in case of the first generation, you are having 1/4 capital A, 1/2 capital A small a, and 1/4 small a plant. So these 1/4 capital A plant will produce 1/4 capital A plant, and 1/4 small a plant will produce 1/4 small a plant. And these 1/2 capital A small a plant will produce, if you will self multiply them, they will produce, if you make the Punnett chart, you can make this Punnett chart and you can see they will produce AA, 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 and small a, So they will produce 1 by 4 capital A, 1 by 2 capital A small a, and 1 by 4 small a plant, but the initial frequency is 1 by 2. So you need to multiply this by 1 by 2 and you will be getting 1 by 8, 1 by 4 and 1 by 8 small a plants. So in the first generation, how many capital A plants you are getting? From this you are getting 1 by 4 and from this you are getting 1 by 8. So in total you are getting 3 by 8 capital A plants or the genotypes in the plant. Similarly, 1 by 4 is small a and you are getting 1 by 8 is small a. So you will be getting 3 by 8 is small a plants. And how much is the heterozygosity? It is 1 by 4. Now what happened in the second generation? These 3 by 8 AA plant will produce 3 by 8 capital A. 3 by 8 small a plant will produce 3 by 8 small a plants. But now this 1 by 4 capital A plant will produce, again these things are going to be same, 1 by 4 AA, 1 by 2 and 1 by 4 as in the case of this Punnett chart. But since the initial frequency is 1 by 4, so you need to multiply it by 1 by 4 and you will be getting 1 by 16, 1 by 8 and 1 by 16. So you can get, if you will join this 3 by 8 AA and 1 by 16 AA, so you will be getting 7 by 16 capital A plant, 7 by 16 small a plant, and you will be getting 1 by 8 capital A small a plant. And this thing will continue for the third generation. Now these 7 by 16 plants will produce 7 by 16 AA, and similarly the 7 by 16 small a plant will produce 7 by 16 small a. Now the initial frequency is 1 by 8, so you need to multiply these things, 1 by 4, 1 by 2 and 1 by 4 to 1 by 8, and you will be getting 1 by 32 capital A, 1 by 16 capital A small a and 1 by 32 small a plant. So you need to combine 7 by 16 capital A plant with 1 by 32 capital A. Similarly, 7 by 16 is small a plant to 1 by 32 small a, and this time the heterozygosity is going to be 1 by 16. So you can see the heterozygosity is decreasing from 1 by 4 to 1 by 8 to 1 by 16. So heterozygosity is decreasing from one generation to another generation in the case of inbreeding. So if you want to do this, it's by the formula. You can do it by the formula as well. So the formula is for calculating the frequency of capital A is this one. So the formula is this one. P1 is equal to P0 plus Q0 by 4 for the first generation. Then Q1 is Q0 by 2. Then R1 is R0 plus Q0 by 4. Here P is the frequency of P is 1 by 4, Q is 1 by 2 and R is 1 by 4, which is capital A, small a and small a. So after one generation, if you will calculate this, the frequency of P is going to be 1 by 4 plus 1 by 8, so it is going to be 3 by 8. Q is going to be 1 by 4 and R is going to be, you will calculate, then it will be again 1 by 4 and plus 1 by 8, it is going to be 3 by 8. Now in the second generation, if you want to calculate, so now you need to again do what? P if frequency is 3 by 8, Q is 1 by 4 which will be 3 by 8 plus 1 by 16, and if you will do this, you will be getting 7 by 16. Similarly, Q you will be getting 1 by 4 into 2, which will be 1 by 8. Similarly, R you will be getting the same thing, which will be 3 by 8 plus 1 by 16, which is 7 by 16. So with this formula also you can calculate the frequency of the genotype, but every time you need to calculate this first, and then in this formula you need to add. This is after first generation, this is after second generation. Similarly, in the third generation, if you are using this formula, then in place of P you need to add the value of 7 by 16. So like this you need to calculate the frequency of genotypes with each generation. And why I am telling this, because the heterozygosity is decreasing in case of the inbreeding from one generation to another generation. So now we will calculate the inbreeding coefficient. Okay, so let's read this. One assumption required for constant allele frequencies under inbreeding is that all genotypes must have an equal likelihood of survival and reproduction, which is to say that no natural selection takes place. Okay, so in this case, however, the heterozygosity is decreasing, the allele frequency is constant. If you will calculate the allele frequency, it is going to be constant, and this is constant because all genotypes must have an equal likelihood. If suppose one genotype is more fit in case of the another genotype, then this rule may not follow. So now the frequency of the heterozygous genotypes in the inbred subpopulation is equal to 2pq. The inbreeding coefficient is expected heterozygosity minus observed heterozygosity divided by the expected heterozygosity. So if you want to see this, F is equal to expected heterozygosity, observed heterozygosity divided by the expected heterozygosity. And if you do some mathematical calculation, you will be getting like H0 is equal to HE minus FHE, or H0 is equal to HE 1 minus F, and or you can say H0 is equal to HE. We have already know 2pq, expected heterozygosity is always 2pq, so you can place instead of HE you can place the 2pq, so you will be getting 2pq 1 minus F. So if you know the frequency of P and Q allele, and if you know the inbreeding coefficient, you can calculate the observed heterozygosity. Now with this note, let's do this problem. So in this population, in a sample of 100 population, there are 14 mm, 32 mn and 54 nm. So now you need to calculate the frequency of M allele, which is going to be 2 into 14 plus 32 divided by total number of population, which is 2n, or 2n is equal to 2 into 100, it will be 28 plus 32 divided by 200, it will be 60 by 200, or you can say 0.30, right? So it will be 0.30. Now the frequency of N allele, if you want to calculate the similarly, it will be 2 into 54 plus 32 divided by 200. So it will be 0.70. If I'm not doing any mathematical errors, I think it is 0.70. So the calculation is going to be done like this. So now you need to calculate the frequency of the expected heterozygosity, which is 2mn. and that is going to be 2 into 0.30 into 0.70, which is equal to 0.42, right? And you are getting basically what, this is your expected heterozygosity, and observed heterozygosity, if you know, that is going to be equal to 32 by 100, which is 0.32. So now you can calculate the inbreeding coefficient F, which is the expected heterozygosity, which is 0.42 minus observed heterozygosity divided by expected heterozygosity, which will be 0.10 by 0.42. And if you want to calculate in percentage, you need to multiply it by 100. So these are the formulas for the allele frequency. And again, if you have not watched my videos on allele frequency, please do watch these videos. It is very clear in them, in those videos. So the frequency of M and N allele you calculate, and then you calculate the heterozygosity. Okay, so this is like 0.42, and this is the heterozygosity which you already observe here. So this is the heterozygosity of the genotype. So we are taking the N number, not the 2N number. Here we are calculating the allele frequency, that is why we have taken the 2N number. Here we are taking the heterozygosity, which is the genotype, so we are taking the N, not the 2N. Okay, because each gene has 2 alleles, so that is why we are taking here the 2N number. So now you calculate the inbreeding coefficient. It will be like 0.10 by 0.42 into hundreds. So detrimental effects of inbreeding, called inbreeding depression, are found in virtually all outcrossing species, and more intense the inbreeding, the more harmful the effects. Okay, so this is the detrimental effects of the inbreeding. And how we can calculate the inbreeding coefficient of the breeding from the pedigrees? The formula is 1 by 2i 1 plus fa, where fa represents the inbreeding coefficient of the common ancestors and I represent the common ancestors. Okay, fa is the inbreeding coefficient and I is the common ancestors. So with this note we can do some. So you can see, in general, if a path through a common ancestor A contains I individuals, the probability of the autozygosity due to that path is going to be equal to 1 by 2 into I raised to the power I 1 plus Fa. Okay, so I is the number of individuals of a through a common ancestor A. So we can do with this note some numericals out of it, so that we can actually understand how to calculate this. For example, if we take this pedigree, if we take this pedigree, let's say A, B, then C, then D, then E, then F, let's say, and then you can say this is like I, and we want to know the inbreeding coefficient of I. Okay, can you calculate it? So there could be two pathway. Let's see this one. So it will be like this: 1, 2, 3, 4 and 5. So common number of individuals, if we are talking about the ancestor of this particular individual, which is I, it is having 1, 2, 3, 4, 5. This is one root, and It could also be this one. This could also be like this one. Okay, and again this is going to be the common. I is going to be the common, so I'm not marking it. So again it will be 1 2 3 4 5. So how you will calculate is 1 by 2, 1 by uh, that will be 1 by 2, 5 plus 1 by 2, 5. So that will be equal to 1 by 32 plus 1 by 32, and you will be getting 1 by 60 is going to be the answer of this pedigree problem. So one pathway, let me highlight this. One pathway is like this. This is one pathway, and the another pathway is from F to D to B to C to E, and the another pathway is F to C to A to D to E, F. Okay, E C A D F and F D B C E. So these are the two pathways. In this pathway, 5 individuals are involved. So therefore we have writing 1 by 2 raised to the power 5. So you can see E C A D F and F D B C E. Okay, so this is one example. Now let's do the some other examples also. So let's do some other example, which is like this one, then again this one, and let's say this one. Okay, so it is going to be, can you calculate the inbreeding coefficient here? Can you calculate it? So if you will see here, if we are writing like, if suppose this is A, B, C, D and I, for I we want to calculate the inbreeding coefficient. So the pathway could be like C, A, D, and pathway could be like D, B, C. So there could be two pathway, and the number of individuals which are involved is 3. So we will be writing 1 by 2 to power 3 plus 1 by 2 to power 3, which will be 1 by 8 plus 1 by 8 is equal to 1 by 4. So this is how we can calculate the inbreeding coefficient here. Okay, similarly there is one more example which you can do it by yourself if you want to do it. If suppose this is a first mating cousin, then it is like brother sister mating. You can say A, B, C, D, E, F and I. Okay, and it is like this, 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 this. It is like this and like this. Can you calculate for this the inbreeding coefficient and the number of paths? So you can see here, one pathway is going to be E, C, F. Another pathway is going to be F, D, E. Okay, another pathway is going to be E, C, A, D, F. Another pathways could be E, C, B, D, F. Another pathway could be F, D, B, E, then it could be F, D, A, C, E. So there are in total 6 pathway. And number of individuals, if you will see here, so it will be 1 by 2 raised to the power 3. Here it is 1 by 2 raised to the power 3. It is 1 by 2 raised to the power 5. 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 You just plus sum of all of these values, so you will be getting like uh, 1 by 8 plus 1 by 8 plus 1 by 32 plus 1 by 32 plus 1 by 32 and plus 1 by 32. So if you will do this, you will be getting 4 plus 4 plus 1 plus 1 plus 1 plus 1, which will be 12 by 32. So if we will do this, 3 by 8. So this is going to be your inbreeding coefficient in this formula. So that's how you can calculate the inbreeding coefficient by the pedigrees. Okay, and there is one more example which I want to give you, is this one. Let's say this is this one, this is this one, this is this one, and this is this one, and let's say this is this one. Okay, so this is like this, 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 and this, and this. So you can see here the pathways are not for this individual. This is not the ancestor. For this individual, this is not the ancestor. So we need to cut it off. So again, the pathways could be 2 only. If suppose this is A, B, C, and this is I. So for the I, if we want to calculate, so pathway could be B, A, and C. Right? There could be only one pathway. So here you can write 1 by 2 into 3, which will be equal to 1 by 8. So that's how you can calculate the inbreeding coefficient by the pedigrees. So I hope this video is clear to you. If you have any other question, you can write it in the comment, and we can discuss some other pedigrees problems also. So thank you for watching my YouTube channel, and if you like the content of my channel, do subscribe my channel, and thank you so much.